Everyone, there are many different controllers we can add to our closed loop configuration. The simplest controller is a proportional control. In this video, we will cover the derivation of equations for a closed loop proportional controller with a first order plan. We will cover part of section 5.2 beginning on page 82 of the notes. How do you think the system response will change when it's in a closed loop configuration? All right, let's get started. So we're going to start here with a proportional controller, which is the simplest controller that we can put in our closed loop configuration. And our transfer function here is simply a gain. And we're going to refer to that gain as K sub P for proportional. And so our block diagram for our closed loop system, based on what we just covered in the previous video, is going to look like this. And so in the next couple slides, what we're going to do is start with g of s being our first order transfer function, and we're going to see how our g of s response changes when we put it into this closed loop configuration and start gaining some insights in how we might use this information to pick a KP that will make our system do what we want it to do over time. And as we progress through chapter 5, we're going to learn more tricks for picking KP, or for also determining that a KP alone might not be a sophisticated enough controller to achieve our desired results. So here we have our first order examples. So our G of S, or our plant, is going to be any first order system. So this could be our DC motor. It could be any first order system that we can think of, and I've got it in time constant form, K over tau S plus 1. And as we talked on the previous slide, our C of S in our block diagram is going to be KP. And the first thing we want to do is find G sub CL, or our closed loop transfer function, which is Y over R. So that's what we're going to do on this slide. So we're going to find G sub CL, which we know is Y over R. And in the previous video, we said that was going to take the form of C times G over 1 plus C times G. And we know what C and G are from the problem statement. So we have KP times K over tau S plus 1. And now as we're doing these, you need to pay attention very closely, because we're going to have multiple Ks in our equations here. So you got to pay attention to your subscripts. And this is going to be over 1 plus our controller, which is KP, times our transfer function, which is K over tau S plus 1. And so we know transfer functions are ratios of polynomials. And right now we've got some complex fractions going on. So let's simplify that a little bit and multiply top and bottom by tau S plus 1 over tau S plus 1. And if we do that, we get KP times K over tau S plus 1 plus KP times K. And while that looks like a transfer function, it's not in time constant form, nor is it in root form. And what I want to do is understand what happens to my time constant after I put it in the closed loop configuration. So I'm going to put this in time constant form by multiplying top and bottom by 1 over 1 plus KPK over 1 over 1 plus KPK, which is my second term there. And if I do that, I get that GCL equals KPK over 1 plus KPK all over tau over 1 plus KPK times S plus 1. So now I'm in time constant form. I have one coefficient of S plus 1 in my denominator, which is my key to being in time constant form. And so now I can fill out table 5.1 and think about what happened to my first order system when I put it in this closed loop configuration. And so my time constant in my original G of S was tau. whatever tau happened to be. It was approximately 0.1 seconds for our DC motor in lab, for example. But now, after I put it in my closed loop system, the time constant of my closed loop system is what I just circled in purple. And we're going to call that tau sub CL for my closed loop tau is now my original tau over 1 plus Kp times K. So what was the effect we have here? So as Kp increases, so if I start adding, making Kp bigger and bigger and bigger, tau closed loop is going to be smaller. And so say my time to steady state was too slow in a particular system and I wanted to speed that up. Well, a proportional controller is going to do exactly that, because as I add more Kp, it's going to decrease my tau, and thus decrease 4 times tau and decrease my time to steady state, which could be very advantageous to our design. But unfortunately, as you've seen with other engineering designs, a lot of these really cool features come with an asterisk. And so what we're going to look at on the next slide is what happens to our error over time and calculate that E over R signal. So now we're going to calculate our E over R transfer function for our G of S and our first order system, and our C of S equals Kp. So we have C equals Kp and G equals K over tau S plus 1. So we're continuing with the first order system from the previous slide. And so now we're going to calculate E over R. And so from the previous video, we said E over R is 1 over 1 plus C times G. And so we have now 1 over 1 plus Kp times K over tau S plus 1. And I'm going to multiply top and bottom again by tau S plus 1 to get rid of my complex fractions. And when I do that, I get tau S plus 1 over tau S plus 1 plus Kp times K. And I'm just going to leave E over R in this form because we don't talk about E over R in the same terms of having it in time constant form or root form, because primarily what we do with E over R is calculate what we call steady state error, and we're going to call that E sub SS, just like we had Y sub SS, now we have E sub SS. So what's going to happen to our error over time, and we can use the final value theorem just like we did for YSS. So this is going to be the lim as S goes to 0 of S times E over R, which we just calculated, and it says R of S is a unit step, so we're going to do 1 over S, and so now we can cancel our S and our 1 over S, and so we're going to do the lim as S goes to 0 of tau S plus 1 over tau S plus 1 plus Kp times K. And if I take that limit, my result is 1 over 1 plus Kp times K. And that is my steady state error. And so what does it mean to have a steady state error of 1 over 1 plus Kpk? Basically what that means is, because it's not 0, is that our Y is never actually going to achieve our exact output as our R. And so we're always going to have a slight difference between R and Y, which may be acceptable because we are engineers, and being within 2% of our final value might be okay because it's inversely proportional to Kp, so we can keep increasing Kp and reducing that steady state error. But let's take a look at what we mean graphically by ESS. So I'm going to draw a set of axes here. So just like always, my x-axis is time in seconds, and my y is my output. And so if I were to plot the signals that we've been talking about. R of S is a unit step, and so it's going to be at 1. So if I draw my legend here, my dark blue line is R of S at 1 because it's a unit step, and we assume that our steps change at time equals 0. And then if I draw here in red my Y of S, that's, if we look at our Y over R, it's still a first order system. It just has a different time constant than our original system. So it's going to look like an exponential increase up to a value. And so this is my Y of S. And then my E of S is the difference between R and Y. And so a non-zero E of S means that my red line for YSS is not going to ever quite reach my R of S, because I'm going to have at steady state a small ESS left over. And so there's always going to be this little bit of difference between R and Y, and that's what our ESS is measuring, because E equals R minus Y, and so ESS is that difference at steady state. And so that's what we're calculating when we're looking at our steady state error, is how much of a space between our output Y and our desired input R do we have once we reach the steady state of our system. So in this video, we've covered what happens to our first order system when we put it in a closed loop configuration with a proportional controller equal to KP, symbolically with any first order system and any controller value KP. And we've talked about both the closed loop transfer function GCL, or Y over R, and our error transfer function E over R, as well as what's going to happen to our error over time and our steady state error ESS. Thanks for watching.